Alright, so welcome to Unit 7 on Atomic Theory. We're going to be spending quite a few videos really walking through our history of our, atomic theory. We're going to be actually going through, starting with a summary of where we actually kind of first hear an atom, and ending with what we know today as a quantum mechanical model, which is basically our modern view. You'll find that this actually took a lot of scientists, but most of this is actually pretty recent. So, here we go. So, the common notion of an atom and its components is a rather recent idea, honestly not even a century old. Most of what we actually know of really was invented 1920s. Not invented, I'm sorry, discovered. I do apologize real quick for this video. It will not have underlines actually in the notes. My hope is that for future ones I will. However, to be honest, I am rather short on time, so I'm trying to get this video now, that way we can use it. Anyways, our modern idea is pretty recent. So, some of the earliest ideas of an atom, however, were around in the 600s BC. These can really be summarized by saying atoms were very small things that comprised everything. Your goal in this section of videos is to be able to tell me, why did we go from Model A to Model B? And there's really 4 or 5 models that we're going to be focusing on. There's probably a couple more, but there's 4 or 5 main famous ones. The earliest one is, this one, which is that atoms were just simply small things. That's really all they had. One of the earliest guys is a guy named Democritus, if you'd like to look him up. But yeah. So, a lot of times I'm also going to make sure you kind of have a visual idea of what this model looks like. So, for the first atomic model, this one's really complicated. Okay, you ready? This is what the first atom looked like to scientists. There you go. It's a small thing. Yeah, that's about it. As you can tell, we had a tiny bit of improvement on this since then. But nonetheless, that's our first model. So, continuing on, in the early 1800s, we next get John Dalton and his atomic theory. There are a few people, quite a few people, between the 600s BC and the 1800s AD. It's more than 2,000 years. Many people looked into atoms, but honestly, John Dalton's the most famous guy, if you will. A lot of other people probably had contributing work, but John Dalton's kind of the most famous, so we're going to talk about him. His theory kind of has 4 main postulates. Number 1, he said that every element is composed of extremely small particles called atoms. Alright, so again, extremely small things. Come on, Dalton. 2,000 years, can't improve on this. Whatever. Number 2, all atoms of a given element are identical, but the atoms of one element are different from the atoms of all other elements. Now, thing you got to realize, especially with postulate number 1, he's actually thinking of these as really small, indivisible things. No protons, no neutrons, no electrons. And so what he says, first off, that should give you an idea if we have an issue. He basically says that every atom of, that's awkward, of atom red, or element red, are going to be the same, and every atom of element blue are going to be the same, but red will not equal blue. Now, we know that different elements are different. It's kind of obvious. What he's forgetting, and by forgetting I mean hadn't been discovered yet, so I guess he wasn't forgetting, are things called isotopes, where we can have, 2 different carbon atoms, both with different mass numbers. So you'll find that John Dalton's very famous because he was wrong, but he was very good. He took a really big step in the right direction, but it really wasn't that significant of a step. It's just, oh look, there's the right direction, we'll take it from here type thing. But there you go, number 2, everything is identical. Unless they're different, then they're all different. Alright, so number 3. Atoms of one element cannot be changed into atoms of a different element by chemical reactions. basically means that atoms are neither created nor destroyed in chemical reactions. Now, this is true until you get to nuclear chemistry, but for now, it's totally true. Carbon's going to stay carbon. It's not going to suddenly turn into oxygen. It's not going to turn into nitrogen. Again, nuclear chemistry changes this because you got the whole radioactive decay. But for now, this is fine. And number 4, compounds are formed when atoms of more than one element combine, meaning a given compound always has the same relative number and kind of atoms. Water is always H2O, not H2O2. So we've talked about these actually in unit 1, I think. But as a reminder, this is basically John Dalton's, and this is 1800s. He's doing pretty well, but there's definitely quite a bit of improvements that can be done on this model. So, for example, in the late 1800s, a lady named Madame Curie, or Marie Curie, her husband, Pierre Curie, I think, and Henry Becquerel discovered the concept of radioactivity. So, I know that doesn't seem at all applicable. We're going from atoms to, yay, uranium. But stick with me for a bit. So, Marie noticed that X-rays, which, by the way, X-rays were discovered a few years earlier than her, like 1895. So this is 1897, 1898. Again, barely more than 100 years ago. Marie's sitting in a lab and she's working, and she basically noticed that uranium, kind of this sample of uranium, was emitting things that were very similar to X-rays. Now, X-rays are a type of radiation. She actually ended up dying because she kind of discovered 2 elements, radium and polonium. And long story short, turns out having samples of radium in your pocket all day kind of, make cancer grow inside you, and she ended up dying because of that. Sad story is her husband died first, and then she carried on her work, and then died because she carried on her work. So, anyway, she's really awesome. Crazy famous. Look her up. She's awesome. But she noticed that this sample of uranium was emitting this radiation. She was like, wait a second, that's weird. Because it's just chilling there. Like, sending out radioactive decay. And she concluded then that those rays had to actually come from the atoms themselves. Now, let's think this through. That means that atoms were emitting something from inside them. Okay, there wasn't a power. They were just sending this thing off, which means if something's coming from inside an atom, that means that A, the atom is partially divisible because, like, there's something coming out of it. There's many sections of it. And secondly, there's something inside it. Like, now she's saying, okay, first off, we've all, she's been operating for about 100 years. Not quite 100, sorry. She's been operating for a decent amount of years, thinking that atoms are just small rubber balls, if you will. And now stuff's coming out of them, and she's like, that's weird, because it's been happening all the time. So, fast forward it, about a year later, a guy named J.J. Thomson had heard of this, and he's like, all right, let's kind of take this a step further. So Thomson used a device called a cathode ray tube. Basically, it's a tube that shoots a ray of cathodes. Okay, that's kind of all you got now. And he revealed actually 3 new types of radiation. He called them alpha, beta, and gamma. Now, we've heard them before. You've heard of gamma rays like in superheroes. Yes, they actually exist. Not quite the same effects that you're thinking of. But J.J. Thomson found these 3 different. And what's weird is he found that the paths of alpha and beta radiation were actually bent by an electric field, which means this radiation, this decay, can be controlled, if you will, can actually be reflected, though in opposite directions, and he found the gamma really didn't do anything, which means that not only are these particles coming out of a atom, like, first off, we've gone from nothing to something coming out of atoms to now there's different types of things coming out of atoms. And Thomson's like, this is freaky. So he ended up concluding that basically because these acted differently, there's these things called charged particles. Okay, he says, I don't know what they are, but one of this is basically kind of some kind of positive charge, and one of these are some kind of negative. They're different. They're opposite. They go to different things. And long story short, he's most credited for finding the negatively charged ones, which today we know as an electron. So we've now gone from a small blob to stuff's coming out of it to especially there's at least this thing called an electron, which you know by now is about the most important particle in chemistry because it's where all our reactions come from. So Thomson then, sorry, this is actually all one sentence. I tried to kind of make it shorter, but it just kind of goes together. Thomson basically then said, okay, we've had Dalton's model for a while, which keep in mind was basically, if you will, this. Okay, and now he's saying there's got to be something in there. Okay, I'm not really sure what. He said there's at least two different things. The gamma radiation didn't really do much, but at least there's two different types of stuff in there. And he again called one positive and negative, and so he said that he developed this plum pudding model, which is, imagine like bread pudding. Think of like an oatmeal raisin cookie or like a chocolate chip cookie, basically some kind of thing where you've got a lot of dough, if you will, and there's things stuck in it, or like a watermelon seed. So he said that the atom consists of a uniform positive sphere of matter. So you've got this sphere of positive stuff in which the mass is evenly distributed. That's important because that's wrong, but you know, at that time we thought it was fine. But in which the electrons are embedded like raisins in a pudding or seeds in a watermelon. So you've basically got this ball of dense stuff, and there's electrons just kind of stuck in there in random places. Completely false. But again, he's saying something's coming out, so maybe there's two different types. So in 1909, Robert Millikan actually confirmed what is called oil drop experiment. He actually confirmed the existence of an electron. So, you know, Thomson wasn't too far wrong. And he actually even found that its charge was equal to 1.602 times 10 to negative 19 coulombs. Keep that in the back of your mind, but you probably don't really need to remember it. Anytime you see that, AP is going to be saying, given this knowledge, you know, perform electrolysis or something. And again, this was actually an oil drop experiment. Vaguely important to kind of keep in mind. He basically put drops of oil into two charged plates and realized, hey, look, they're attracted, and then did some math with it. So let's kind of wrap this up. Let's show you what a plum pudding model looks like. So plum pudding model, I'm going to try and draw with a circle, so hang on just a second. Okay, so for no obvious reason to me, the circle is red, but whatever. Basically, he's saying here's an atom, and this whole stuff, if you will, is basically positive. So think of like the cytoplasm in a cell where it's like the stuff surrounding everything. He's saying this is surrounded by positive stuff. And inside this positive stuff are electrons. Okay, they're kind of just stuck in there. Again, they're not moving. They're just stuck surrounded by positive stuff. That is the plum pudding model, one of the very first famous models that is completely wrong. But again, we've gone from a solid blob of nothing to a blob with some stuff in it. There you go. That wraps up our video. And that is our first section of atomic theory.